All right, let's dive right in. We're about to tackle one of the biggest, most mind-bending questions you can possibly ask. And we're going to use real, hard science to explore an idea that honestly sounds like it's been pulled straight out of a movie. And here it is. Is our reality, everything we see, touch, and feel, just an incredibly advanced, high-fidelity simulation? I know, it sounds pretty wild. But supporters of this idea say we don't have to look far for a model of how it could work. In fact, you might have one sitting in your living room.
So, let's start there. Think about how a modern video game can create these enormous, breathtaking worlds without, completely frying its hardware. Well, the secret is all about efficiency. It's about being smart with your resources.
Okay, so check this out. A game is clever. It only renders or draws what you, the player, are actually looking at. That mountain way off in the distance, it's just a low-quality placeholder until you get closer. This saves a ton of computational power. So the theory goes, what if our universe does the exact same thing? What if it only renders the specific state of a particle at the very moment it's being observed? I mean, that would be an unbelievably efficient way to run a simulation the size of a universe.
And this is where things get really interesting. This isn't just some philosophical question to ponder. This is something we can actually investigate in a laboratory. We can put this idea of a reality that's rendered on demand to the test. Our main tool for digging into this is one of the most famous and, frankly, most baffling experiments in the history of science, the double-slit experiment. But before we get to the weird part, we have to lay down the ground rules for how the world is supposed to work, according to common sense.
Okay, so the rules are pretty simple, right? If you shoot solid objects, think of them like tiny little marbles, through two parallel slits, you'd expect to see two solid lines on the wall behind them. They act like bits of matter. But if you send a wave through, like a ripple in a pond, the wave splits, and the two new waves interfere with each other. This creates a really distinct, spread-out interference pattern. So, particles make two clumps, waves make a spread-out pattern. Easy enough?
So let's be clear. An electron has mass. It's a fundamental particle. It's matter. So if we fire electrons through our two slits, based on everything we know, we should absolutely see two neat, clean lines on the detector. It's just common sense. End of story, right?
Yeah, you can probably guess where this is going. What actually happens is anything but common sense. This is the moment where reality seems to just take its own rulebook and toss it right out the window.
And here it is, the first absolutely mind-blowing result. We fire particles, but what we get on the screen is a full-blown interference pattern, a pattern that can only be made by a wave. The electrons, these tiny bits of matter, are somehow acting like waves and interfering with each other. This just shouldn't be happening.
So at first, scientists thought, okay, maybe the electrons are just bumping into each other, causing this weird pattern. It's a logical guess. So they slowed the whole thing down. They fired just one single electron at a time. No way they could interact now. But over time, as the single electrons hit the screen one by one, that impossible wave pattern slowly built up again. It's as if each individual electron went through both slits at the same time as a wave and interfered with itself.
This is just bizarre. So the logical next step for any scientist is to say, all right, let's just look. Let's put a tiny detector right at the slits and actually see which one the electron goes through. We'll solve this mystery once and for all.
And this is the absolute kicker. The moment they placed the detector at the slits to watch, the wave pattern completely vanished, gone. And what was left? Two distinct clumps, exactly what we expected from particles in the first place. When you stop looking, the wave pattern comes back. It's as if the universe, or the particles themselves, know they're being watched.
Okay, if your brain isn't already hurting, let's take this to a whole new level of strange. The physicist John Wheeler proposed an even weirder experiment, one that suggests our observation might not just change the present, it might actually change the past.
So get this. In this version, you let a photon pass through the slits, while it's still in its undefined wave-like state. You only decide to turn the detector on after it's already gone past them, and the result is just reality breaking. The moment it's observed, its own history appears to be rewritten. The photon is recorded as having gone through one specific slit, like a particle, even though the decision to measure it happened after the event.
And this effect isn't just some tiny quirk that happens on a lab bench. The implications are, well, literally astronomical. What happens when the distances aren't just a few millimeters, but millions and millions of light years?
I want you to just take in this number for a second. 100 million years.
That's how long light has been traveling from a distant galaxy to reach our telescopes here on Earth.
This leads us to this bonkers concept called retrocausality. It basically means an effect can happen before its cause. Our decision, right here, right now, to measure that ancient photon as a particle appears to instantaneously change the state it was in when it left its source, 100 million years ago. An action in the present seems to be altering the distant past.
So, what on earth is going on? How do we make any sense of this? Well, this is where we circle all the way back to our very first idea. What if these bizarre quantum rules aren't bugs in the universe? What if they're actually features of its programming?
When you look at it through that lens, all of a sudden, it kind of starts to click. The universe only renders definite properties when an observer is present, to save cosmic processing power. The speed of light isn't just a speed limit, it's the processing speed of the whole system. And all this quantum weirdness, like changing the past, it's just the program executing code, updating variables based on new input. And it doesn't care about the linear flow of time that we experience inside of it.
And look, this isn't just some wacky idea from the fringes of the internet. There are prominent physicists who, when they start to view the universe as a giant system of information, find the simulation hypothesis to be a pretty compelling explanation for what we're seeing in these experiments.
Which leaves us with this one final, really unsettling thought. These experiments seem to tell us that a particle doesn't have a definite state until we look at it. So if you scale that idea all the way up, it poses a pretty profound question about the nature of, well, everything. If our universe only bothers to render what's being observed, what's actually there when we're not looking?